Welcome to Part B. Now we get into the training dynamics, the knobs that decide how a fine-tune actually behaves. Cross-entropy, learning rate, batch size, LoRA, GPU memory, reading loss curves, evaluation, decoding, dataset formats, and how to avoid breaking your model on narrow data. 12 lessons. Then Track 2 turns it into Python. Cross-entropy is the loss for next token prediction. For each completion token, the model produces a probability distribution. The loss is the negative log of the probability the model assigned to the correct token. Lower loss equals higher confidence in the right answer. This is exactly the SFT objective. Perplexity is cross-entropy in friendlier units, the average number of tokens the model was choosing among. Learning rate is the size of each weight update. Too high, the optimizer overshoots. Too low, it crawls. Sensible ranges for LoRA on small instruct models, 1e-4 to 2e-4. Warmup ramps the rate up over the first few hundred steps to prevent early instability. Then a decay schedule, cosine is the standard, eases it back towards 0. Epochs and steps both work, pick the one natural for your dataset size. Batch size controls the gradient smoothness. Larger batches average over more examples, so the gradient is steadier and the optimizer takes more confident steps. If you cannot fit a big batch in GPU memory, use gradient accumulation. Accumulate gradients over several small forward-backward passes, then take one optimizer step. The number that matters is effective batch size, per device batch times accumulation times devices. Full fine-tuning updates every weight. Powerful, expensive, large memory, the whole model changed. LoRA trains a tiny add-on instead. Small low-rank matrices that sit alongside the base weights, capturing the change you want. The base stays frozen. The adapter is a few megabytes. Keep it separate for swapping, or merge it into the base for shipping. The trade-off is small in capability and huge in cost. 4 LoRA knobs. Rank R controls adapter capacity. Common values are 8, 16, 32. Alpha sets how strongly the adapter speaks. A typical rule is alpha equals 2 times R. Target modules pick which layers get adapters, usually the attention query and value projections. Dropout is light regularization against overfitting. QLoRA is LoRA on a 4-bit quantized base, so a much larger model fits the same memory. GPU memory has 4 consumers: model weights, gradients, optimizer state, and activations. For full fine-tuning, every parameter has a gradient and an atom W state. Memory is roughly 6 to 8 times the model size in FP32. Mixed precision in BF16 halves that. Activations grow with sequence length and batch. Gradient checkpointing trades compute for activation memory. When you OOM the levers in order. Reduce batch size, raise gradient accumulation to keep effective batch, enable gradient checkpointing, lower max sequence length, switch to BF16 if you were not already, then consider QLoRA. Each step costs something, usually compute time. Auto-retry on OOM tools exist, but they hide a sizing mistake. Size the run honestly the first time instead. 3 shapes of loss curves. Healthy, training loss falls, eval loss falls both flatten. Overfitting, training loss keeps falling but eval loss rises, the model is memorizing. Underfitting, both losses are high and not moving, usually a wrong learning rate or not enough data. Respond honestly. Overfit means more data or fewer epochs, not more compute. Underfit means the model needs a real signal to learn from. Pick a metric that fits the task shape. F1 or accuracy for classification, exact match or span F1 for extraction, faithfulness for generation. Always compare to a baseline. The lift over the untuned base is what your training bought. Gates decide the bar in advance. A fine-tune ships only if it clears them. Evaluate on the gold set, never the test split. Decoding is not training. Same model, different decoding settings, very different outputs. Greedy, take the most likely token. Sampling, draw from the distribution. Temperature softens or sharpens, top P and top K truncate the tail. Set a stop token and a max new tokens cap. Honest beat, repetitive output can be a decoding bug or overtraining. Try repetition penalty 1.1 or nucleus sampling first. If variety returns, decoding. If not, retrain on more diverse data. The dataset you receive is rarely the shape the trainer wants. JSONL is the standard container, one JSON object per line. Inside, common shapes are prompt completion, chat messages, alpaca, share GPT. Conversions are mechanical. Alpaca to chat messages is 5 lines. The conversion matters because the trainer's built-in chat template and loss mask code only runs if the input shape is right. Catastrophic forgetting is what happens when you optimize for narrow data and lose broader capabilities. SFT is especially susceptible. Your dataset is hundreds of rows, per training was trillions. Mitigations: prefer LoRA base weight stay untouched. Mix in 5 to 10% broad instruction data. Stop early. Eval broadly. Honest beat, smaller models forget faster. The right epoch count for a 7B is not the right epoch count for a 135M. That ends track 1. You now have the full SFT conceptual stack: data, mask, loop, dynamics, evaluation, decoding, and the failure modes. Track 2 takes all of this and turns it into runnable Python: environment, dataset, the LoRA trainer loop, eval, and shipping. See you there.